our channel Learn with us. In this video, we are going to discuss about semaphores. First of all, we learn about what does synchronization means. Now I'm going to discuss about synchronization. Synchronization is nothing but it is the process of coordinating multiple processes to ensure that they do not interfere each other and work together to accomplish a task such as accessing shared resources such as memory or files. Why synchronization is important? What is the purpose of synchronization? To coordinate multiple processes. So without synchronization, concurrent processes can interfere each other, leading to incorrect results. It ensures that shared resources are accessed in mutually exclusive manner and prevents data races. Synchronization in simpler terms means synchronization is like making sure multiple things happen in right order or at right time. Let's get into our topic semaphores. Semaphores are synchronization tool. It is an integer variable or abstract data types used to control access to shared resources in a concurrent system. They act as signaling mechanism which allows process to request and release access to resources to maintain order. Here, it is the important point that when a process wants to access resource, it must first acquire the semaphore. There are two operations in semaphore, wait operation P and signal operation V. Wait operation. If the semaphore's value is greater than 0, the process can access the resource and the semaphore's value is decremented. If the value is 0, then the process must wait until the semaphore's value becomes greater than 1. Then signal V operation. Once a process finished using the resource, it must release the semaphore which increment the semaphore's value.
Now we are going to see about types of semaphores. We have already seen that what is semaphores. Semaphores are integer values that are used to solve critical section problem. There are two types of semaphores. One is counting semaphores and the another one is binary semaphores. Let's see what is counting semaphores. A counting semaphore is represented by an integer value that can be incremented or decremented by the processors, and it has an unrestricted value domain. That means values between minus infinity to plus infinity. They maintain the count of available resources and allow the processes to acquire and release resources. These semaphores are used to coordinate the resource access, where the semaphore count is the number of available resources. If the resources are added, semaphore count automatically incremental, and if the resources are removed, the count is decremental. If no resources are available, the process will be blocked until a resource become available. Let's see what is binary semaphores. It can be used to enforce mutual exclusion for a critical section in user code. Binary semaphores are like counting semaphores, but their value is restricted to 0 and 1. Binary semaphores have two operations, that are wait and signal operations. Both operations are atomic. Atomic means that the variables on which we modify and update happens at the same time with no preemption. The wait operation only works when the semaphore is 1, and the signal operation succeeds when the semaphore is 0. The major reason behind introducing binary semaphore is that it allows only one process to enter into a critical section if they are sharing resources. The key difference between binary and counting semaphores is that the binary semaphores can only take on two values, indicating either that your resource is available or unavailable, while counting semaphores can take on multiple values, indicating the number of available resources. In semaphores, there are two operations. One is wait and the another one is signal. Here, inside the wait function, there is a while loop with condition s less than or equal to 0. Note that there is a semicolon after while. It implies that the code gets stuck here while s is 0. In other words, we can say it will wait until s equal to 0. Here, the wait operation decrements the value of its argument s if it is positive. If s is negative or 0, then no operation is performed. In signal operations, semaphore value will be incremented. Now, we are going to see the implementation of semaphores. Before knowing about the implementation of semaphores, we need to know what is process and what are threads. A process is not executing a program. A thread is the unit of execution within a process. A process can have anywhere from one thread to many. Let's see how acquiring and releasing semaphores happens. Thread can acquire a semaphore by calling the wait function, which decrements the semaphore value. When a thread is done using a shared resource, it releases the semaphore by calling the signal function, which increments the semaphore value. Let's see about semaphore initialization when implementing semaphores. Semaphores need to be initialized before they can be used. It involves setting the initial value of the semaphore, which determines how many threads can access a shared resource at the same time. If any process that wants to access the shared resources, they have to first execute the entry section, where the wait operation decrements the value of the semaphore. If the value of the semaphore is 0, that means all the resources are in use, and now onwards the process trying to execute the entry section would be blocked. Let's see how entry section code works. In this implementation, the wait function decreases the value of the semaphore S. If the resulting value is less than 0, it implies that the resource is currently unavailable and the process needs to be blocked. The process is then added to the queue associated with the semaphore. If the value of the semaphores is positive, then the process returns without being blocked. Let's see how execute section code works. Now, when a process wants to release the resource, then it has to execute the exit code before releasing the resource. Executing the exit code, the process increments the value of the semaphore with the signal operation, unblocks a blocked process and thereby release the resource. The unblocked process can now try to execute the entry section code to access the resource. There is always a waiting queue linked with each semaphore. The processes are unblocked or removed from the waiting queue in the first in first out manner. That means the processes that have been waiting for a long time is released first. Now let's see the advantages of using semaphores. Mainly semaphores are used for synchronization. They ensure orderly execution of a program, they prevent the race condition and maintain the program integrity. Other advantage of using semaphore is coordination. Semaphores are like signals that different parts of a program can use to work together and stay organized. So semaphores can be used for signaling. They also allow processes to wait when a resource is not available, avoiding busy waiting, and it can save the CPU cycles. Semaphores are like adaptable tools that can be used in many ways to help manage multiple things happening at the same time in your program. So, semaphore achieves flexibility and is also a versatile tool in multi-threading and multi-processing environments. Now, let's jump into the disadvantages or cons of using a semaphore. So, the major disadvantage is the complexity. Semaphore introduces complexity in our code. So, the potential for bugs in your code arises if it is not used correctly. Then, when the semaphores are improperly managed, it can lead to deadlock where the processes get stuck and cannot make any progress. Semaphore also gives overhead, that is, semaphore requires some extra work for the computer which can slow down a program. When the issues arises, debugging problems related to semaphore can be tricky as they involve timing and race conditions. Despite the disadvantages of semaphores, they have various advantages making them widely used.
Best practices of semaphore. When working with semaphores, it's crucial to follow some best practices. First one is error handling. Implement error handling mechanism to deal with any issues related to semaphore usage such as waiting indefinitely or resource leaks. Then resource protection. Use semaphores to protect critical resources, preventing multiple threads from accessing them simultaneously and causing data corruption. Then concurrency control. Employ semaphores to control access to shared resources, ensuring that only one thread can access a specific resource at a time to avoid race conditions. Then avoiding busy waiting. Utilize semaphore along with efficient waiting mechanisms such as conditional variable to prevent threads from wasting resource through busy waiting. Then testing and debugging. Test your code thoroughly to ensure that the correct functioning of semaphore and use debugging tools to identify any potential issues. Following these best practices will help you effectively to manage concurrency and synchronization using semaphore in your code.